Hello everyone, I am Christian and I am with my friends Nishchal and Sagar are going to present the paper Tagging English Text with a Probabilistic Model by Bernard Merialdo. This work lies in the domain of natural language processing, specifically in part of speech tagging. Before going into technical aspects, let us understand the core problem. Suppose we have been given a sentence and we want to assign a grammatical tag such as noun, verb, or adjective to each word. However, this is not trivial because many words are ambiguous. For example, play can be a noun or a verb depending on context. So the key challenge is how do we use context to correctly disambiguate tags? And this paper addresses that using probabilistic modeling. Let us now understand the abstract and the claim given in the paper. The paper studies POS tagging using a probabilistic model and compares two parameter estimation approaches. First, relative frequency, which uses hand tagged data, and second, maximum likelihood, which uses untagged data. Now, an important clarification is that the novelty of the paper is not a new model or a decoder, whether the actual novelty is using untagged text during training and evaluating whether it actually improves the performance or not. Now the key result is very important because the more hand tag data we have seen best tagging accuracy, and in ML training it improves perplexity but can reduce accuracy, and this leads to a fundamental insight that model objective is different from evaluation objective, and this separation is one of the most important conceptual contributions of the paper. Now, talking about existing approaches and shared observation, this paper situates itself among the three approaches. First, rule-based systems, where we use manually written grammar rules. Second, probabilistic systems, which is data-driven. And third is early neural methods. Now, a key empirical observation is that each word has only a small set of plausible tags. For example, the almost is always a determiner, and run is can either be noun or a verb. So the problem is not unconstrained classification. Instead, it is selecting the correct tag from a small set, which is disambiguation. Next point is local context resolves ambiguity, meaning the surrounding tags help decide the correct tag. That's why transition probabilities, in other words, tag sequences are essential. Finally, probabilistic framework is useful because it formalizes assumptions and enables learning from data and also allows ranking of alternatives. Now, let's discuss why the probabilistic formulation is useful. First, if probabilities can be estimated, then the system can be trained instead of manually built, and this reduces reliance on handcrafted rules. Second is same model works for both tagged and untagged data, and this is crucial because tagged data is expensive and untagged data is abundant. And the third, the main motivation is practical, that can be reduce annotation cost by using untagged data. And the fourth one is the paper does not claim probability is perfect. Instead, it claims that probability makes the problem measurable and computationally manageable. Now, if we talk about defining problem, then let's go step by step. First, a sentence is represented as a capital W, which represents a sequence of words, and uh, and we have a tag sequence represented by capital T, which is of same length as of capital W. And this pair W comma T is called an alignment. And now a tagging procedure selects one alignment for each sentence. And there are two evaluation levels. First is sentence level, entire sequence must be correct. And second at word level, which evaluate that whether individual texts are correct or not. And the important insight is sentence level is stricter, so paper uses word level accuracy. This slide introduces the core mathematical idea. First, we have assumed a joint probability distribution P of W comma T. And now for sentence level evaluation, we need to choose a T that maximizes probability of W comma T, which is a Viterbi decoding. And for word level evaluation, we need to choose a tag with a maximum posterior probability per position. This is ML tagging. An important note is that Viterbi is standard even though it is not optimal for word level accuracy. It is because it is simpler and produces a consistent sequences and also computationally efficient. This slide defines the tri-class model. The full model factorizes into one word generation probability and second tag transition probability. Now key approximations are that tag depends only on previous two tags, that is trigram assumption, and the second is word depends only on its tag, that is emission assumption. This approximation reduces complexity and make models trainable. Now let's talk about model size, free parameters and dictionary constraints. Now first, here NW is the vocabulary size and NT is the number of tags. And transition parameters are given as NT cube and emission parameters as NW into NT. But due to normalization constraints, effective free parameters are reduced and final formula is given as NW minus 1 into NT plus NT minus 1 into NT square. And important takeaway is that model grows linearly with vocabulary size, which proves that the model is also scalable. And also one important thing is dictionary specifies valid tags for each word, and if a tag is impossible, probability is set to 0. And this helps in reducing computation and improving accuracy and also prevents invalid sequences. Now we are moving to training part, and the two approaches that have been used are first is relative frequency training, which uses hand tagged text and directly counts observed word tag and tag trigram events. And the second one is maximum likelihood training, which treats the tag sequence as a hidden and uses only the word sequence, which turns the problem into hidden Markov model training. And important point is that this use fundamentally different information sources, and this sets up the central comparison of the paper. Now let's go deeper into relative frequency training and its limitation. First is relative frequency estimates are just count ratios, and as we discussed, we compute probabilities directly from observed counts. And this works very well when we have sufficient data and observation cover most of the cases. So this method is simple, interpretable, and have a strong baseline. But most critical point is that any unseen sequence will get the probability 0. Now this is a serious problem because let's suppose we have an example in which in training data we have never seen a text sequence like noun, verb, and then adjective. Then its probability becomes 0. Now consider a new sequence where this sequence actually occurs. Then the entire probability of that text sequence will become 0. And since we multiply probabilities across positions, one 0 will kill the entire sequence. So we have just seen that a 0 inside the product can kill the entire alignment. So even if the 99% of the sequence is correct, one unseen event can result a total probability to be 0. And this makes the model fragile, unable to generalize, and also overfitted to the training data. And that is why we have the paper has introduced smoothing, and this leads to the next slide where we will discuss smoothing. And one of the important insight is that smoothing is a very important concept in NLP and ML in general because models based purely on observed data fail to generalize. That's why we need smoothing to handle unseen events. This slide explains how we fix the zero probability problem. The first method is we smooth using interpolation with uniform distribution. The idea is simple but yet powerful. Instead of relying only on observed data, we combine it with a uniform distribution. So probability becomes final probability equals to lambda times observed probability plus 1 minus lambda times uniform probability. Meaning is that if data is reliable, we trust on observed counts, and if data is sparse, we fall back to uniform. The second method is interpolation coefficient is chosen by deleted interpolation. Now the key question is, how do we choose lambda? We don't just pick it randomly. Instead of that, we split data into training and held out set. We try different values of lambda and choose the one that performs best on held out data. And this is called deleted interpolation. And we use observed distribution when reliable and fallback when sparse. This is the intuition behind smoothing. For example, common words will give reliable count so we can trust on them, but rare words are unreliable so we use fallback. So smoothing balances the trade-off between bias versus variance. And the fourth point is more elaborate schemes exist. The paper mentions count-dependent interpolation, lower-order models, and back-off strategies. This shows smoothing is a broad and important topic in NLP. So to summarize, RF alone will result in zero probability problem. Smoothing fixes this issue, and interpolation balances data and uncertainty. And this makes the model robust and usable on real-world data. Now that we have understood how relative frequency training works, let us move to the second approach, maximum likelihood training, which is conceptually more involved. The core idea in this approach is that we do not use tagged data, instead we only observe word sequences. So for a given sentence W, the tag sequence T is unknown as it is hidden. This makes it a hidden Markov model. Now let's connect this to HMM. We assume tags follow a Markov process and words are generated from tags. But tags are not directly observed, so this is exactly a hidden Markov model, where hidden states are tags and observations are words. Now what are we trying to optimize is that we want to maximize probability of the entire training corpus, mathematically maximize the product of P of W over all sentences. But P of W equals to sum over all possible tag sequences T of P of W comma T. So instead of one correct sequence, we consider all possible tag sequences. Now, why is this difficult? Because the number of possible tag sequences grow exponentially with sentence length. So we cannot compute it directly. Now the solution is forward-backward algorithm. To handle this, we use forward-backward algorithm. This algorithm efficiently computes expected counts, iteratively updates parameters, and guarantees improvement in likelihood. ML training is theoretically elegant, but it optimizes likelihood of word sequences, not tagging accuracy. And this difference becomes very important later in experiment. So in ML training, tags are hidden. We learn indirectly using probabilities, and the objective is likelihood, not accuracy. Now that we have trained the model, the next step is to actually assign tags to new sentences. The two tagging approaches are discussed in the paper. Like first is Viterbi tagging. This finds the single best tag sequence for the entire sentence. Formally, it selects T that maximizes P of W comma T. And how does it work? It works using dynamic programming. It efficiently explores possible sequences and finds the most probable one. And some of the advantages are it produces globally consistent tag sequence and it is also linguistically meaningful. Second is maximum likelihood tagging, which is also a word level tagging. Here, instead of selecting the full sequence, we select the best tag for each word individually. So for each position, we choose the tag with highest posterior probability. Now difference between the two is that in Viterbi, we do sequence level optimization, and in ML tagging we do word level optimization. And even though ML tagging aligns better with evaluation word accuracy, Viterbi is more commonly used because it is simpler, more stable, and produces valid sequences. So there is a trade-off of global consistency versus local optimality. Now let's briefly discuss a computational complexity. Viterbi algorithm using dynamic programming. This ensures efficient computation despite large number of possible sequences. And second point is that at first glance, ML tagging seems more complex because it involves summing over many possible alignments. But because of a HMM structure, these computations can also be organized efficiently using forward-backward style recursion. So final takeaway is that both Viterbi and ML tagging have linear complexity in sentence length, so they are computationally feasible in practice. So even though the problem seems complex, the model structure allows efficient algorithm. Now that we have understood both training methods, RF and ML, their underlying assumptions and how tagging is performed, the next important question is how do these methods actually perform in practice? For that, Nishal will now take over and explain the experimental setup and results.
Now I will begin with the experimental section of the paper. Before analyzing results, it is very important to understand the dataset and setup used in the experiments. First part is the dataset source. This paper uses the tree bank or Associated Press corpus. This is manually annotated dataset, meaning each word in the dataset already has a correct POS tag assigned. This ensures that we have reliable ground truth for evaluation. Second part is the dataset size. Total corpus size is 42,186 sentences. The training set has 40,186 sentences and the test set has 2,000 sentences. So majority of data is used for training and a separate portion is used strictly for testing. This separation is important to ensure fair evaluation without overfitting. The third part is the tag set. Originally we had 159 tags, but we reduced it to 76 tags because a smaller tag set reduces complexity and makes result more stable and interpretable. Fourth part is the dictionary construction. The dictionary is built directly from the corpus, meaning for each word only those tags are allowed which were observed in data. This is important because it eliminates impossible tag assignments and improves efficiency and accuracy. So overall, this setup ensures realistic data, controlled evaluation, and reduced ambiguity through dictionary constraints. Now that we understand the dataset, we can analyze how the training method perform. Now we move to the first major experiment, relative frequency training. This table shows how performance changes as we increase the amount of labeled data. First observation is that accuracy increases rapidly with more labeled data. For example, with 0 sentences, accuracy is low. With 2000 sentences, accuracy jumps significantly. This shows even a small amount of labeled data gives large improvement. Second observation is that interpolation coefficient lambda increases. This coefficient controls smoothing. As data increases, we trust observed frequencies more, so lambda increases. Third observation is that improvement becomes smaller at higher data. From 10,000 to 20,000 to full dataset, the improvement is marginal. This shows diminishing returns. This tells us that most learning happens early and after a point adding more labeled data gives limited gains. Now let's carefully analyze the actual numbers in this table. Step-by-step interpolation. 0 sentences give 77% accuracy. This is basically random but still high because many words have only one possible tag. 100 sentences give 90% accuracy. This shows huge jump with very little data. 2000 sentences give 95.4% accuracy. This shows already very strong performance. And full dataset gives 97% accuracy. So just 2000 labeled sentences already achieve near optimal performance. This is extremely important because it shows that labeled data is very powerful. Interpolation trend shows that lambda increases from 0 to 0.94, meaning as data grows, model relies more on actual counts than smoothing. So this table establishes a strong baseline. RF training is highly effective when labeled data is available. This slide gives a deeper interpretation of table 1. First point is that first few thousand sentences do most of the work. Means initial data gives major improvement and larger data gives small gains. Second point is that 2000 sentences give error rate less than 5%. This is already very strong performance. And third point is that difference between 20,000 and full data is small. This shows saturation effect. Final point is that this motivates next question. If more labeled data gives limited gains, then can we use untagged data instead? And this leads us to the next set of experiment using maximum likelihood training. Now we move to maximum likelihood training experiments. Initial setup is that we start from a uniform model, meaning all tag sequences are equally likely initially, except dictionary constraints still apply. We observe that ML training improves perplexity but also reduces tagging error initially. Important point is that accuracy is still much lower than RF with small labeled data. Lower perplexity does not guarantee better tagging accuracy. This is one of the central messages of the paper. So ML is improving the model internally, but not necessarily improving the actual task performance. Now we analyze ML when starting from weak models. The setup is initial models trained with 0 sentences, 100 sentences, and 2000 sentences. Then ML training is applied. We observe that for weak models, ML improves accuracy significantly from 77% to 86.6%. ML helps when initial model is poor because it learns structure from large unlabeled data. So ML is useful as correction mechanism for weak models. Now let's see what happens with strong initial models. Initial models with 5,000, 10,000, 20,000 and full data. Accuracy starts decreasing after ML iterations. When model is already strong, ML hurts performance because ML optimizes likelihood, not tagging accuracy. So it shifts probabilities in a way that improves word prediction but worsens tagging decisions. This is the most important experimental result of the paper. This figure visualizes results from table 2. The top curve, low data, improves over iterations. Bottom curve, high data, degrades over iterations. So the same algorithm behaves differently depending on starting point. This clearly shows ML is not universally beneficial. This slide summarizes implications. ML training is only helpful when the relative frequency initializer is weak enough that the hidden Markov re-estimation can repair it. Once the supervised model is already accurate, ML starts pushing probability mass toward a better word sequence model that is not necessarily a better tagger. The paper explicitly distinguishes perplexity from tagging accuracy. Improving one does not guarantee improving the other. That is the central reason the paper treats ML as a plausible but dangerous training method for tagging. Finally, we will compare decoding methods. The difference between Viterbi and ML tagging is very small. Means choice of decoding algorithm is less important and training data quality matters more than decoding model. With this, we conclude the experimental analysis. Now Sagar will explain further insights and conclusions.
Now we begin with an interesting observation from the experiments. The first point states that the model produced during ML iterations are related. This means that ML training gradually updates the parameters, so the successive models are not drastically different. Because of this, the outputs of Viterbi and ML decoding remain similar. The second point states the error rate gap is very small, even though Viterbi optimizes sequence level probability, ML optimizes word level probability, but in practice their performance is almost the same. The third point states that the main story is not about decoding. Uh, this is very important because this paper emphasizes that the key factor is how the model is trained and not how the decoding is done. Next, the practical takeaway is that Viterbi gives coherent sentence level interpretation while ML aligns with evaluation metric. but both are overshadowed by training data quality. So this slides tells us that don't not to focus too much on decoding tricks, but to focus on better training data and estimation methods. Now the authors try to fix the problem with ML. ML was found to degrade strong models, so the question becomes, can we restrict ML so it doesn't damage a good model? So if a model has too many parameters related to data, it can overfit or move in wrong directions. So constraints are introduced to keep estimates close to reliable values, and the key idea is to not allow ML to freely modify everything. Instead, preserve parts of the model that are already well estimated. This is an attempt to balance the flexibility and stability of the model. Let's look at the first constraint method. What is TW constraint? It keeps probability of T given W fixed for frequent words, meaning if a word appears very often, its tag distribution is already reliable, so we should not change it during ML training. And the observation is that standard ML degrades accuracy quickly, while the TW constrained ML degrades more slowly. So interpretation is constraint reduces damage but does not eliminate it. This shows that constraint help in stabilizing learning, but they do not solve the problem fully. Let's understand why this constraint works partially. First point states that frequent words have reliable statistics, so their probabilities should not be disturbed much. Uh, Second point explains error increases more slowly. This confirms constraint is effective in stabilizing the model. This is still worse than RF baseline, so even with constraint, ML cannot outperform supervised learning. This is a diagnostic experiment, meaning it helps us understand the problem, but it is not a final solution. So, constraint improve ML slightly, but do not change the overall conclusion of the paper. Now we move to another type of constraint. What is T constraint? It keeps overall tag distribution probability of T fixed, meaning the frequency of tags like noun, verb, adjective remains unchanged. Why it is harder is that tags distribution depends on model parameters indirectly, so it is more complex to enforce. So it is only applied to a simpler bi-class model. And observation is that again degradation is slower than standard ML but still worse than RF baseline. This reinforces the same pattern. Constraint help but cannot overcome the core issue. Now let us analyze the deeper meaning. The first point is that fixing tag distribution preserves important structure because RF already estimates this well. Improvement is modest, so problem is not just over parameterization. The core issue is that mismatch between perplexity and tagging accuracy. This is the root cause. And the final note is that experiments are limited, but the conclusion remains consistent. This slide strongly reinforces that the problem is fundamental, not just technical. This slide summarizes all the methods. Relative frequency, best accuracy when enough label data is available. Standard ML can use untagged data but often degrades accuracy. Constrained ML better than standard ML but still not better than RF. So the final hierarchy is that RF is best, ML has limited use, constrained ML is partially good. This clearly answers the main question that the labeled data is more valuable than unlabeled data. Now we reach the final conclusion of the paper. The key points are more hand tag data gives best accuracy, ML improves perplexity but not accuracy, ML helps only when initial model is weak. So practical recommendation is that we should use as much label data as possible and not do not assume untagged data will replace it. This is very practical and somewhat surprising conclusion. This slide translates results into actionable steps. First, we should get as much hand tag data text as possible because the supervised counts dominate every other method in paper when enough data is available. Second, if labeled data is scarce, ML on untagged data may help, but only as a way to improve a poor initial model rather than a universal replacement for annotation. Third, keep the dictionary constraint because impossible tags should not be allowed to receive probability mass. Fourth, the evaluation target is tagging accuracy, not perplexity. The two objectives can disagree. Let's quickly summarize the model mathematically. The model is a joint distribution probability of W comma T, and approximations are trigram tag model, emission model. Training is RF gives direct counting, ML is hidden variable estimation. Smoothing ensures robustness for unseen events. We can see the various formulas used in this slide. This slide summarizes the broader impact. The paper is historically important because it ties together probabilistic modeling, hidden Markov training, and empirical evaluation on realistic tagging corpus. Its strongest message is not to untagged text is useless, but that untagged text training is not automatically better than supervised count for POS tagging. It also explains why a clean objective such as perplexity is not enough when real task is tagging accuracy. That distinction is reason the paper is still cited. It is a careful empirical warning against confusing model fitting with task performance. Thank you.
Hi everyone, today we will be presenting the paper Efficient Estimation of Word Representation in Vector Space by Thomas Mikolov and his team at Google. Now this paper is considered as one of the most influential works in modern NLP. In fact, it introduced what we widely know as word-to-vec, which completely changed of how machine understand language. Before this work, most NLP system treated words as completely independent symbols. That means king and the word queen has no inherent relationship inside the model, even though as humans we clearly understand that they are related. But this paper introduced a new way of thinking. Instead of treating words as discrete symbols, it represents them as continuous words in a high dimensional space. Now this might sound simple, but it leads to very powerful outcomes. These vectors are not just random numbers, they actually capture meaning, similarity, and relationship between words. For example, relationships like king minus man plus woman would technically equal to queen, that it would be easily capturable in this model using simple word vector arithmetic. This shows that the model is not just memorizing words, but actually learning underlying linguistic patterns. In another important aspect of this paper is efficiency. Earlier, natural language models were powerful but extremely slow and computationally expensive. This paper solves that problem by introducing simpler architectures that can scale to billions of words. So, in this presentation, we will not just explain what word2vec is, but also understand why earlier methods failed, what key idea led to this breakthrough, how CBOW and skipgram models work, how optimization techniques make training feasible, and finally, why this paper had such a huge impact on NLP. So, with that, let's move on to the motivation behind the work. Let's begin by understanding the motivation behind this paper. In traditional NLP systems, words are treated as atomic units. Each word is simply represented as index in a vocabulary with no concept of similarity or relationship between words. Now, this design choice actually had some advantages. It made some models simple, easy to implement, and quite robust. For example, n-gram models, which are widely used in language modeling, can be trained on extremely large datasets, even trillions of words. However, this simplicity comes at a cost because these models completely ignore semantic meanings. To represent words numerically, we typically use something called one-hot encoding. Let's say we have a vocabulary of 10,000 words. Each word is represented as a vector of size 10,000, where only one position is 1 and all other positions are 0. So essentially, every word is orthogonal to every other word. This creates two major problems. First, these vectors are extremely sparse and inefficient, as most of the values are 0, which wastes memory and computation. Second, and more importantly, these vectors do not capture any similarity at all. For example, if we compute similarity between cat and dog, we get 0. But if we compute similarity between cat and table, we also get 0. So the model has absolutely no way to understand that cat and dog are more related than cat and table. This is a major limitation. To address this, researchers introduced count-based methods like co-occurrence matrices, which look at how frequently words appear together. For example, if coffee and cup appear together often, they are considered related. While this is better than one-hot encoding, it struggles to capture deeper relationships and become inefficient for very large datasets. Another important limitation mentioned in the paper is data availability. In some domains like speech recognition, we only have limited high quality labeled data. Similarly, in machine translation, many languages do not have very large corpora. So simply scaling up traditional models does not always lead to better performance. Then came neural network based language models, which introduced distributed representation of words, meaning words are represented as dense vectors, and these models performed significantly better than traditional n-gram models. However, they had a major drawback. They were computationally very expensive, and training them on large data sets could take weeks.
So now we reach the key motivation of this paper. We want a model that learns meaningful word representations, captures semantic and syntactic and relationships, scales to massive data sets, and is computationally efficient. In simple terms, the goal is to get the best of the both worlds. The efficiencies of simple models and the representational power of neural networks. And this is exactly what this paper achieves by introducing simple yet powerful architectures that can learn high quality word vectors from billions of words efficiently. Now that we understand the motivation, let's move to the core idea behind this paper. The entire approach is based on very important concept of linguistics known as the distributional hypothesis, which states that you shall know a word by the company it keeps. In simple terms, this means that word which appears in similar contexts tend to have similar meanings. This idea might sound intuitive, but it is extremely powerful when applied at scale. Let's understand this with an example. Consider these two sentences. The cat is sleeping on the bed and the dog is sleeping on the bed. If we look at the context of the word cat, we see words like is sleeping on bed. Similarly, for the word dog, we see almost the same surrounding words. So, from the model's perspective, cat and dog share very similar context. And this is exactly where the model tries to learn. Instead of explicitly defining relationships, it learns them automatically from data. But here is the key shift introduced by this paper. Earlier approaches were mostly count based, relying on counting how often word appears together. This paper introduces a predictive approach. In a predictive model, we train the system to perform tasks like given a context, predict the target word, or given a word, predict its surrounding context. And while solving this task, the model learns vector representations for word automatically. What makes this interesting is that these vectors captures multiple types of relationships, not just basic similarity, but also more complex patterns. For example, semantic similarity between king and queen, syntactic similarity between run and running, and even relational patterns like country capital relationship. Another important point is that word similarity is not just one dimensional. Word can be similar in different ways. Big and large are similar in meaning, but big and bigger are related syntactically. And the model is able to capture all these multiple degrees of similarity within the same vector space.
So instead of manually designing features, we let the model learn everything directly from data. This shifts from counting to predicting and from discrete to continuous representation. It is the key innovation of this paper. Now that we understand the core idea, let us see how this idea is actually implemented in practice. To implement this idea, the paper introduces two main model architectures. First, continuous bag of words or CBER, and second, skipgram. Both of these models are designed to learn word embedding efficiently, but they approach they approach the problem in slightly different ways. In CBER, we take the surrounding context words as input and try to predict the center word. For example, consider the sentence, the quick brown fox jumps over the lazy dogs. If our target word is fox, the model will use context words like quick, brown, jumps over to predict fox. Skipgram does the exact opposite. Instead of predicting the center word, it takes the center word as input and tries to predict the surrounding words. So if the input is fox, the model will try to predict quick, brown, skip over. In short, SIBA goes from context to word, while skipgram goes from word to context. Another key choice in both models is simplicity.
Unlike earlier neural networks, these models remove the non-linear hidden layer. This might seem like a limitation because non-linearity usually helps model learn complex patterns. But here, removing it is a major advantage. It, it drastically reduces computational complexity, and because the models are simpler, they can be trained on much larger datasets. This is actually one of the main contributions of the paper. Instead of making the model more complex, they made it simpler and scaled the data. Also, both models use a projection layer, meaning all words are mapped into the same vector space. During training, these vectors are continuously updated based on prediction errors. Over time, words that appear in similar contexts end up having similar vector representation. So even without explicitly defining similarity, the model learns it automatically.
So to summarize, Seabow and Skipgram are two simple yet powerful architectures that implement predictive learning idea. They are designed to balance efficiency, scalability, and representation quality. Now that we have a high-level understanding, let's dive deeper into each model, starting with Seabow. Now let's go deeper into the first model, CBOW, which stands for Continuous Bag of Words. The main idea is simple. We use the surrounding context words to predict the center word. Let's take a concrete example. Consider the following sentence. The quick brown fox jumps over the lazy dog. Suppose our target word is fox. If we choose a window size of 2, we take 2 words before and 2 words after. So the context becomes quick brown jumps over. Each of these words is first converted into a vector from an embedding matrix, which is learned during training. Then, instead of processing them separately, we combine them into a single representation, usually by averaging or summing the vectors. This is where the term bag of words comes from. The model does not care about the order of the words, whether a word comes before or after the target, or its exact position is ignored. Only the presence of words matters. This is both a strength and limitation. It makes the model simpler and faster, but it loses information about word order. Once we have the combined context vector, we pass it through the model to predict the probability of each word in vocabulary. So essentially, CBOW is solving a multi-class classification problem. The correct word in this case is fox. It should get the highest probability. And during training, we adjust the word vectors so that correct predictions become more likely. Over time, over time, words that appear in similar contexts get similar vector representation. So the model naturally learns semantic similarity. CBOW is also very efficient since we combine multiple context words into a single vector. We make only one prediction per training example, and since the architecture has no non-linear hidden layer, computation is significantly reduced, allowing the CBOW to be trained very fast on even on large datasets. CBOW works particularly well for frequent words since common words appear many times. The model gets enough training examples to learn them well. However, CBOW has a limitation. It does not perform well for rare words because rare words appear less frequently and the model gets fewer opportunities to learn their representation. So, to summarize, CBOW is fast, efficient, and good for frequent words, but it ignores the word order and is not ideal for rare words. Now, let's move on to the second model, which tries to address some of these limitations.
The second model is skipgram. Unlike SIBO, skipgram takes a single word as input and tries to predict its surrounding context. So it reverses the direction of prediction. Let's use the same example. The quick brown fox jumps over the lazy dog. If our input word is fox and the window size is 2, the model will try to predict quick brown jumps and over. Now here is an important difference. In SIBO, we made one prediction using multiple context words, but in skipgram, we make multiple prediction for a single word. So one word generates several training examples. For instance, fox, quick, fox, brown, fox, jumps, fox over. This increases the amount of training data significantly, and this is one of the key reasons why skipgram performs better for rare words. Even if a word appears only a few times, each occurrence produces multiple training samples, so the model still gets enough signal to learn good representations. Another interesting idea mentioned in the paper is that not all context words are equally important. Words that are closer to the target word are usually more relevant. So during training the model sometimes give less importance to distance word either by sampling few distant words or by assigning them lower weight. Now let's talk about the trade-off. Skipgram generally produces better embeddings, especially for rare and less frequent words, and it captures fine-grained relationships better because it learns from individual word context pair and preserves more detailed informations. But this comes at a cost. Since we generate multiple predictions per word, the computational cost is higher compared to SIBO. In practice, skipgram with negative sampling become one of the most popular choices because it balances quality and efficiency well. So to summarize, skipgram is better for rare words, produces higher quality embeddings, and captures detailed relationships. But it is more computationally expensive depending on the use case. We choose between SIBO and skipgram. Now that we understand both models, let's move on how these models are actually trained and what objective functions they optimize.
Now that we understand SIBO and skipgram, the next question is what exactly is the model trying to optimize? In simple terms, the goal of both models is to maximize the probability of making correct predictions. SIBO tries to maximize the probability of predicting the center word given its context, while skipgram tries to maximize the probability of predicting context words given the center word. So fundamentally, both models are learning by predicting. To do this, we use a function called softmax. Softmax takes a set of scores and converts them into probabilities. So far, every prediction, the model assigns a probability to every word in the vocabulary. Let us understand what this means in practice. Suppose our vocabulary size is 1 million words. For a single prediction, the model has to compute probabilities for all 1 million words and then identify which word is most likely. Now imagine doing this for every word in a large data set. This becomes extremely computationally expensive because for each training step, we need to calculate scores for every word in the vocabulary. The complexity of this operation is proportional to the vocabulary size, which we denote as O of V. And when V is very large, this becomes the main bottleneck in training. Another issue is that most of these computations are unnecessary because in each training step, we only care about the correct word and a small set of incorrect words. But softmax forces us to compute probabilities for all words. So while softmax is mathematically correct, it is not practical for large scale training. And this is exactly where the optimization technique comes in. These techniques are designed to reduce computational while still learning high quality embedding.
So to overcome the computational challenge of softmax, the paper introduces two key optimization techniques, hierarchical softmax and negative sampling. Let's start with hierarchical softmax. In this approach, instead of treating all words independently, we organize them in the form of a binary tree. Each word is represented as a leaf node in this tree, and predicting a word means traversing a path from the root to that word. So instead of computing probabilities for all words, we only compute probabilities along this path. Since a binary tree has a height of log of v, the complexity reduces from O of V to O of log of V. This is a huge improvement, especially considering the vocabulary size is very large. However, the performance of this method depends on how the tree is constructed. A well-balanced tree gives better performance. Now let's move forward to the next technique, negative sampling, which is actually the most widely used technique in practice. The idea is very intuitive. Instead of updating all words in the vocabulary, we only update a small subset of words. For each training example, we take a correct word as a positive sample and a few randomly selected incorrect words as negative samples. So instead of solving a multi-class classification problem, we convert it into a binary classification problem, where the model learns to increase the probability of the correct word and decrease the probability of the incorrect words. For example, if the correct word is fox goes to jump, we might sample negative words like table, car, apple, and train the model to distinguish uh, between them. This drastically reduces the competition between because we only update a few word vectors per step instead of entire vocabulary. Negative sampling also works very well in practice, especially for very large data sets. And that's why the most of the implementations today use skipgram with negative sampling. So to summarize, hierarchical softmax reduces complexity using a tree structure, and negative sampling reduces competition by updating only a few samples per training step. Both techniques make it possible to train a word embeddings efficiently on massive datasets, and And this efficiency is one of the biggest contributors of this paper.
Now that we understand the models and optimization techniques, let's look at how training actually happens in practice. The model is trained using a sliding window approach over the text corpus, meaning we move across the text word by word, and for each word we generate training examples based on its surrounding context. For example, if we have a sentence like the cat sat on the mat, we take each word as the center and generate context pairs dynamically. So the dataset is not fixed. It is generated on the fly during training. This is very important because it allows the model to efficiently use large datasets without storing all training pairs explicitly. The training is done using stochastic gradient descent or SGD. This means we update the model parameters after each training example instead of waiting for the entire dataset. Because of this, the model learns continuously and efficiently. And since we use techniques like negative sampling, each update is very fast. Another key factor is scalability. Because the model is simple, no deep layers, no complex computations, it can be parallelized easily. The paper mentions that they were able to train high quality words vectors on billion of words in less than a day, which was a huge breakthrough at that time. Compared to earlier neural models, which could take weeks, this was a massive improvement in efficiency. The paper also highlights that increasing the dimensionality of vectors and increasing the amount of training data both improve performance. So there is a trade-off between vector size, training time, and accuracy. But overall, this model made large-scale training practical, and that is why word-to-vec became so widely adopted.
Now let's look at the result, which is one of the most exciting part of this paper. The author evaluates the quality of word embedding using analogy tasks, which tests whether the model can capture relationships between words. The most famous example is king minus man plus woman is equal to queen. This shows that the model understands gender relationships, but it goes beyond just gender. The model can capture many types of relationships. For example, in many terms of country capital relationship, Paris is to France as Berlin is to Germany. In terms of verb transformations, run map to running and walk maps to walking. In terms of adjective forms, big maps to bigger and small maps to smaller. These relationships are discovered using simple vector arithmetics. We take vector differences and additions and then find the closest word in vector space. This is extremely powerful because it shows that the model has learned structured knowledge about language. Another important point mentioned in the paper is that these embeddings capture semantic relationships, meanings, and syntactic relationships, grammar. To evaluate this properly, the author creates a comprehensive test set with different types of analogy questions. The model achieved very high accuracy on these tasks, especially when trained on large datasets with high dimensional vectors. This clearly shows that simple architectures can still learn deep linguistic patterns, and this was surprisingly the most important finding of the time.
So to summarize, this paper introduced simple yet powerful models for learning word representations.
These models are highly efficient, scalable, and perform better than previous approaches.
However, they also have limitations like ignoring word order, assigning only one vector per word. But overall, this work laid foundation of modern NLP models. Thank you.
Hello everyone. Today we are going to explain a very important paper in natural language processing titled GLOVE, Global Vector for Word Representation by Jeffrey Pennington, Richard Soccer and Christopher Manning from Stanford University. Before we go deep into the model, try to think of a simple question. How do machines actually understand the language? When we say a word like king or queen, we instantly understand the meaning. But for a machine, it is just a text. So, the entire goal of this paper is to convert words in a form that machines can understand while preserving their meanings and relationships. Now, let's understand why we even need word embeddings. We cannot directly feed text into machine learning models, so we convert the words into numbers. But Not just any number. We want these numbers to carry some meaning. For example, we want the model to understand king and queen are related, or run and running are syntactically connected. Earlier methods like one hot encoding failed because they simply assign unique indices to words, but they do not capture any relationship between them. So even though two words might be very similar, their vector representation might be completely different. That's why we need dense and meaningful representation, which we call word embeddings. Now, the idea becomes more interesting when we look at relationship between words. Words are not independent, they exist in relationship with other words. For example, king and queen share a gender relationship, and let's say Paris and France, they share capital country relationship. What is fascinating that these relationships can actually be captured mathematically using vectors. A famous example is king minus man plus woman gives a vector close to queen. This shows that embeddings are not just storing words but actually learning the structure of language. So the goal is not just representation but also capturing the relationship in a geometric space. Before GLOVE, there were two main approaches to learn word embeddings. The first one is global methods such as latent semantic analysis. These methods looked at the entire data set at once, and they build large matrices like word to word or word to document matrices. They capture overall statistics of the corpus, which is good, but they often fail to capture fine grained relationships like analogies. And then the second approach is local methods like word to vec. These methods focus on small context window and try to predict nearby words. They are very good at capturing relationships and analogies, but they ignore the global statistical structure. So essentially, one method captures global information but misses details, and the other one captures local details but misses the bigger picture. So naturally, we ask a question: can we combine the strength of both? Can we design a model that uses global statistics but also captures meaningful relationships like word to vec? That is exactly what Glove does. It bridges the gap between global and local methods, giving us the best of both worlds. The core intuition of Glove is actually very simple. It says that the meaning of a word can be understood by looking at the words that appear around it, not just in a small window but across the entire corpus. Instead of predicting context like word to vec, Glove focuses on co occurrence statistics, basically, how often words appear together. The key idea is that up, the words that appear in similar context will have similar meanings, and this pattern can be captured using statistics over the entire dataset.
Now let's build this intuition more concretely. If we want to capture meaning, we can count how often pairs of words appear together. For every pair of words, say word I and word J, we count how often J appears near I. This gives us a co-occurrence matrix. This matrix is extremely powerful because it captures global relationships in the data. It tells us not just whether words are related, but how strongly they are related based on frequency. However, raw counts have a problem. Some words like the or is are called stop words and they appear very frequently and can dominate the counts. So instead of using raw counts, we normalize them into probabilities. Specifically, we compute the probability that a context word K appears near a target word I. This makes the representation more meaningful and comparable across different words. Now we come to the most important idea in the glove paper. Instead of using probabilities directly, glove uses ratio of probabilities. This might seem like a small change, but it is actually very powerful. The ratio tells us what distinguishes one word from another. Instead, instead of asking how often a word appears, we ask how its relationship compares between two different words. Let us understand the idea of ratio probabilities with a simple example. Consider the words ice and steam. Now take context words like solid, gas, and water. The word solid is strongly associated with ice, while gas is strongly associated with steam. Now, if we look at the ratio of probabilities, we see that ratio is large for solid with respect to ice, but small for gas. But for a neutral word like water, the ratio is close to 1. This tells us that ratios are very effective at capturing meaningful distinctions while ignoring irrelevant information. This is the key insight that Glove builds upon. Now we want to encode these ratios into vector representations. So we define a function that takes a word vector and context vectors and tries to model the ratio of probabilities. The goal is to learn vectors such that these ratios are preserved in vector space. This is where the transition from statistics to vector representation happens. Let us look at the vector formulation. To model this mathematically, Glove uses vector differences and dot products. The difference between word vectors captures differences in meaning, and the dot product captures how related a word is to a context. After simplifying the equations, we arrive at a very elegant result. The dot product of two vectors is approximately equal to the logarithmic of their co-occurrence count. This is a beautiful connection between linear algebra and probability. To make the model more flexible, we add bias terms. These biases help capture additional factors like word frequency and context frequency that are not fully explained by the vectors alone. So the final model predicts the log of co-occurrence using a combination of vector dot product and bias terms.
Now, how do we train the model? We define a loss function that measures the difference between predicted values and the actual log co-occurrences. The goal is to minimize the difference. So essentially, we are fitting our model to match the real world statistics. The better the fit, the better the word embedding. But not all word pairs are equally important. Some occur very rarely, some occur very frequently. If we treat them equally, the model can become unstable. So, Glove introduces a weighing function that balances their importance. It ignores zero co-occurrences, reduces the impact of rare pairs, and then prevents the frequent pairs from dominating. This makes the training even more robust. Now we come to final word representation. Each word is actually represented in two ways. Once as a target word and then second time as a context word. These two vectors capture different aspect of meaning. So in the end, we combine them to get a final embedding. This gives us a richer and more complete representation of each word. Let's talk about efficiency. If we naively compute the full co-occurrence matrix, the complexity would be very high. It would be the order of a square of vocabulary size. But Glove optimizes this by using sparse matrices and ignoring the zero entries. This significantly reduces the computation and makes the model scalable. Looking at the experimental setup to evaluate the model, Glove was trained on very large datasets like Wikipedia, gigawords, and Common Crawl with vocabulary size of around 400,000 words, and the context window was used around each word. Then forming the co-occurrence matrix using context window over the corpus. The evaluation was done using tasks like word similarity, word analogy, and name entity recognition. These tasks helped measure the semantic and the syntactic understanding. When we evaluate a word embedding model like glove, we do not just check accuracy in a traditional sense. Instead, we test whether the model actually captures the relationship between words in a way that matches human intuition. That is why the paper evaluates on three important types of tasks: word analogy, word similarity, and name entity recognition. In word analogy task, Glove has achieved 75% of accuracy. It outperforms the models like Word2Vec and SVD models, and it captures both semantic and syntactic relationship. In word similarity task, tested on datasets like WordSim 353, MC, and RG, Glove produces similarity scores that closely match human judgment, showing that it captures semantic meanings effectively. In named entity recognition, it helps identifying entities like people, location, and organizations more accurately, which improves real world NLP applications. Overall, these results show that Glove not only performs better than models like Word2Vec and SVD, but also produces embeddings that are more meaningful and practically useful. This slide shows how Glove performs on the word analogy task under different settings. In the first graph, as we increase the vector dimension, accuracy improves quickly at first, then starts to level off. This means larger vectors capture more meaning, but after a point, increasing size gives very small improvements. In the second graph, we vary the window size with symmetric context, meaning we look at the words on both sides equally. As the window size increases, performance improves because the model gets more contextual information. And in the third graph, we use asymmetric context where the context is not balanced on the both sides. This trend is similar. Accuracy still improves with window size, but then there are slight variations compared to symmetric context. Overall, the key takeaway is that context and large vector size improve performances, but only up to certain point, after which gain becomes smaller.
Now let us understand how these different factors affect Glove's performance. First, vector dimension. As we increase dimension, the model can capture more complex relationships, so performance improves. But after a point, around 200 to 300 dimensions, the improvement becomes very small because the model has already learned most useful patterns. Next is the context window size. A smaller window focuses on nearby words which help capture syntactic information like grammar. A larger window captures broader context, which helps in understanding semantic meaning. So, depending on the task, we choose the window size accordingly. Finally, the corpus size matters a lot. Large datasets give better co-occurrence statistics, which improve embeddings, but quality is as important as the quantity. Let us now summarize the advantages of Glove. Glove efficiently captures both global and local relationships, which makes its embedding more meaningful. It produces vectors that reflect real world word relationships, including analogies. Another advantage is efficiency. Since it uses a co-occurrence matrix and focuses only on non-zero entries, training is faster compared to many predictive models. Overall, it provides a good balance between performance and computational cost. Now, let's clearly compare glove with word to vector because this helps us understand where glove actually stands. Starting with word to vector, it is a predictive model. What it does is it learns word embeddings by trying to predict nearby words using a small context window. So essentially, it focuses on local context. It uses models like skipgrams or CBOW along with techniques like softmax or negative sampling. Because it is learning from small windows repeatedly, it becomes very good at capturing local patterns. and it also converges faster during training. On the other hand, GLOVE takes a very different approach. Instead of predicting words, it uses global co-occurrence matrices, which means it looks at how words co-occur across the entire corpus. Rather than focusing only on nearby words, it captures relationships using probability ratios, which allows it to encode the overall structure of the language. Because of this global view, GLOVE often produces more stable and meaningful embeddings, especially for semantic relationships. However, since GLOVE relies on building and processing a large co-occurrence matrix, its convergence is relatively slower compared to word-to-vec. So, in simple terms, you can think of word-to-vec as learning from local context step by step, while GLOVE learns from big picture of the entire dataset. Here on the left side, we are comparing GLOVE with CBOW, and on the right side, GLOVE with skipgram. The y-axis represents accuracy and the x-axis represents training progress. If you observe both graphs, the first thing you'll notice is that GLOVE's curve rises quickly and then stabilizes at a higher accuracy. This means GLOVE is able to learn strong word representations efficiently and consistently. In comparison, CBOW and skipgram models show more fluctuations and generally achieve lower accuracy. CBOW in particular seems less stable and performs worse as training progresses, while skipgram performs better than CBOW but still does not consistently matches GLOVE's performance. Another important observation is that GLOVE maintains stable performance even as training continues, whereas the other models depend more heavily on tuning parameters like negative sampling. So, what this tells us is that GLOVE benefits from using global co-occurrence information, which gives it a more reliable understanding of word relationships instead of relying only on local predictions. And this leads to the key takeaway written below. The GLOVE can be seen as a global version of the skipgram model because it combines statistical information from entire corpus with semantic understanding. Despite its strength, GLOVE has some limitations. It produces static embeddings, meaning each word has only one representation, regardless of any context. So it cannot distinguish between different meanings of a word like bank. Bank can refer to the institution where we save our money or a river bank. It also requires building a large co-occurrence matrix which can be memory intensive for very large datasets and corpuses. Additionally, it does not handle rare or unseen words well. To conclude, GLOVE provides a very elegant solution to the problem of word representation by combining the strength of both global statistical methods and local context based learning. Instead of relying only on predictions or raw count, it uses co-occurrence probabilities and their ratios to capture meaningful relationships between words. This allows it to learn embeddings that are not just mathematically sound but also linguistically meaningful. Because of this balance between theory and practical performance, GLOVE produces embeddings that are stable, interpretable, and efficient, making them highly useful for a wide range of NLP tasks. Overall, GLOVE is not just a model but an important step towards understanding how language structure can be captured in vector space, and it continues to influence many modern approaches in NLP even today. So, this was all for our paper GLOVE.
Hello everyone, I am Krish and I with my friends Nishchal and Sagar. Today we will be presenting the paper Chain of Thought Prompting Elicits Reasoning in Large Language Models. This work explores a very important question that can we improve reasoning ability in LLM without retraining them by just changing how we prompt them. So the answer proposed in this paper is yes, and it is also shown that by using something called chain of thought prompting, which introduces intermediate reasoning steps before the final answer. Now, let's first understand the paper at a high level. The core idea is to include step-by-step reasoning in the prompt examples instead of just input-output pairs. Now, if we think why is this needed, so even though the large language models scale very well, they still struggle with arithmetic reasoning, common sense reasoning, and symbolic reasoning. So the authors ask, instead of modifying the model, can we modify the prompt? So the key result is very strong. With just 8 chain of thought examples, Palm 540B achieves state-of-the-art performance on GSM 8K, even beating fine-tuned models. This shows that prompt design alone can unlock hidden capabilities of large models. Now, let's formally understand the difference between the baseline and the proposed model. In standard prompting, the model directly maps input to output, and no reasoning is shown. This works for simple tasks, but fails when multiple reasoning steps are needed. In chain of thought prompting, each example includes input, then reasoning steps, and final answer. The model learns to generate reasoning first and then answer. So instead of compressing reasoning into one step, we explicitly guide the model through intermediate steps. And this is the key conceptual shift of the paper. To understand the intuition, let's think about how humans solve the problems. Now, if we think about how we solve a math problem, then first we break it into smaller steps, and then we solve intermediate parts, and then combine them. This paper also leverages the same idea. Now, previous approaches tried methods like first training models with explanations, but it was very expensive. And the second method was few shot prompting, which was weak for reasoning. But the chain of thought combines both. It gives reasoning examples without retraining. And the method has four major advantages. First one is decomposition of complex problems. Second is interpretability of reasoning. Third is a generality across tasks. And fourth one is simplicity of implementation. So it is both powerful and practical. Let's now see how this works in practice. In standard prompting, only final answer is given, and in chain of thought prompting, intermediate reasoning steps are explicitly written. Like for example, instead of saying the answer is 11, we explain how many balls were added, how they were calculated, and then we will give the final answer. This teaches the model how to think, not just what to answer. Importantly, no fine-tuning is done and only prompt examples are changed. So this is purely an in-context learning technique. To evaluate this idea, authors test across multiple model families like GPT-3, Lambda, and Palm, and multiple sizes from millions to hundreds of billions. They also test on 5 arithmetic datasets like GSM 8K, SVAMP, SDiv, and two other also. And they have also compared standard prompting versus chain of thought prompting and other variants. So this ensures that the results are not dataset specific or model specific. So the evaluation is quite comprehensive. Before interpreting results, this slide summarizes the different benchmark datasets used in the paper. This is important because each dataset evaluates a different type of reasoning ability. Like if we talk about arithmetic benchmarks, then we have GSM 8K, which covers complex multi-step math word problems, SVAMP, SDiv, variations of arithmetic reasoning, Aqua, multiple choice maths questions, and MAWPS, which includes both simple and multi-step arithmetic. This datasets primarily test numerical reasoning and step-by-step computation. If we talk about common sense benchmarks, then we have like CSQA, which have a general world knowledge, strategy QA, multi-hop reasoning, and date understanding, temporal reasoning, and a few others also. This test reasoning using real world knowledge. And we have also symbolic benchmark like last letter concatenation and flip tracking. This test structured rule-based reasoning. So overall, the paper evaluates COT across arithmetic, common sense, and symbolic reasoning. And this diversity is important because it proves that chain of thought is not limited to a single domain and it is a general reasoning technique. Now, if we look at the arithmetic results, uh, accuracy of all models, then this table shows one of the strongest results in the paper. Across all models, chain of thought improves performance significantly. For example, GPT-3 15.6 to 46.9, Codex 19.7 to 63.1, and Palm 17.9 to 56.9. And these are very large improvements. So what does this tell us? Reasoning ability is already present in the model, but it is not activated by standard prompting. So chain of thought act as a trigger for that ability. Now, this slide highlights three very important insights. First one is chain of thought is an emergent ability. It works only for large models and not small ones. Second is that larger gains are seen for harder problems. Multi-step task benefits the most. And third is it competes with fine-tuned models despite using no training data. So the key takeaway is prompting alone can match supervised learning in some cases. Now that we have understood the method and its core results, the next step is to analyze how and why this improvement happens across different model scales and experiments. For that, Nichelle will now take over and explain the deeper experimental insights.
This figure is extremely important because it reveals a fundamental property of large language models. We observe two very different regimes. For small models, chain of thought prompting either does not help or even degrades performance. The generated reasoning is often fluent but logically incorrect. For large models, there is a sharp improvement in performance. The reasoning becomes more structured and accurate. This leads to the concept of emergent ability. Emergent ability means a capability that does not exist in small model but suddenly appears at larger scale. So reasoning is not gradually improving, it emerges after a certain threshold of about 100 billion parameters. This is a key insight of the paper that you cannot predict large model behavior from small model results. Now, this table gives numerical evidence for the emergence phenomena. If we carefully observe, models below 10 billion parameters often perform worse with COT. Around 60 billion to 100 billion parameters, performance starts improving. At 175 billion and above, we see major gains. Now the question is, why does this happen? Because small models can generate language fluently, but they cannot maintain logical consistency across multiple steps. Whereas large models can track dependencies, maintain intermediate states, perform multi-step reasoning. So chain of thought acts as a test of reasoning capacity. Only sufficiently large models pass this test. Now, this is one of the most critical slides in the paper. The authors are asking a question: what exactly causes the improvement? So they test four hypotheses. First hypothesis is equation only. Maybe the benefit comes from writing equations. Result, it does not work well on complex dataset like GSM 8K. Reason is that mapping natural language to equation itself requires reasoning. Second hypothesis is that variable compute only. Maybe the benefit comes from using more tokens, meaning more computation. So they replace reasoning with dots. Again, the result is no improvement, and conclusion is that more computation alone is not sufficient. Third hypothesis states that reasoning after answer. Maybe reasoning is just helping access knowledge. So they place reasoning after the answer. Again, the result is no improvement, and conclusion is that reasoning must be used before answering. So the final conclusion is that the improvement come from step-by-step natural language reasoning before the answer. This is the central mechanism behind COT. This table confirms the ablation findings quantitatively. We observe chain of thoughts roughly doubles performance in some cases, and all other variants remain close to baseline. Now let us look at robustness. Different annotators, writing styles, example sets, but all still outperform baseline. This shows the method is not fragile. However, small variations still cause some differences. So prompt engineering still matters, but the core idea is stable. This slide highlights an important practical issue. Few short prompting is known to be highly sensitive to prompt design, but the paper shows even with different annotators, different reasoning styles, and different examples, chain of thought still consistently improves performance. This indicates the benefit comes from structure of reasoning, not exact wording. However, there is still some variance. So prompt design matters, but chain of thought is robust enough for real use. Now, in this slide, we move beyond arithmetic into common sense reasoning. These tasks require world knowledge, multi-hop reasoning, and context understanding. For example, strategy QA requires combining multiple facts, and sports reasoning requires domain understanding. Results show chain of thought improves performance significantly. Example, sports reasoning even surpasses human baseline. This is very important because it proves chain of thought is not domain specific. It works because reasoning in natural language is a general capability. Now we will look at how chain of thought performs on these tasks. Overall trend shows that across most datasets, chain of thought improves performance, but the improvement depends on task complexity. The observations are CSQL shows small improvement because baseline is already strong and reasoning depth is limited. Strategy QA shows clear improvement because it requires multi-step reasoning. Date understanding shows large improvement because intermediate steps help track time correctly. Sports understanding show very strong improvement because it even surpasses human baseline in some cases and because chain of thought helps check logical consistency. SECAN shows strong improvement because tasks require sequential planning. Finally, the benefit of chain of thought increases with reasoning complexity, so simple tasks show small gains and complex tasks show large gains. This confirms that chain of thought is especially useful when problem required structured step-by-step reasoning, not just direct answers. Now we will move to symbolic reasoning, which is slightly different from previous tasks. Unlike arithmetic or common sense reasoning, these tasks do not depend on real-world knowledge. Instead, they test logical consistency, step-by-step state tracking, and manipulation of symbols. The paper considered two tasks. First is the last letter concatenation. Here the model must take a sequence of words, extract the last letter of each word, and concatenate them. Second is the coin flip task. In this task, we start with a coin in a given state. Multiple people either flip or do not flip it. The model must track the state step by step, so this becomes a sequential reasoning problem. Now the key experimental setup is that the model is trained on short sequences but tested on longer sequences. This allows us to evaluate whether the model can generalize beyond seen examples. Chain of thought helps by explicitly representing each intermediate steps. So instead of guessing the final state, the model tracks the process step by step. Now let's look at the results of these symbolic tasks. For example, similar to training, large language models with chain of thought achieve near perfect accuracy. Standard prompting performs significantly worse. This shows chain of thought enables correct step-by-step execution. Out of domain results. This is the most important part. Here, the model is tested on longer sequences than seen before. We observe standard prompting fails completely. Chain of thought still performs reasonably well and improves with scale. This indicates that the model is not just memorizing patterns, instead it is learning a generalizable reasoning procedure. Chain of thought enables length generalization, meaning the model can apply the same reasoning steps to more complex or longer inputs. So overall, these results show that chain of thought improves not just accuracy, but also the ability to generalize reasoning, which is a very strong indication of improved reasoning capability in large language models. Now, we will look at this table, which compares different prompting strategies across multiple tasks. It includes standard prompting, chain of thought prompting, and variants like equation only or other modified prompts. First observation is that chain of thought consistently outperforms standard prompting. This shows that adding reasoning steps improves performance. Second observation is that alternate variants do not match chain of thought. For example, equation only and extra tokens without reasoning. These fail to achieve similar performance. So it is not just more computation, it is not just equations, it is the natural language reasoning process that matters. Third observation is that gains vary across tasks. Larger gains means tasks requiring multi-step reasonings and smaller gains for simpler tasks. This reinforces earlier observation that chain of thought works best when reasoning complexity is high. This table acts as a summary validation of the paper's claim full chain of thought prompting is the most effective strategy. Now, the authors manually inspect outputs to understand behavior. They find most correct answers have correct reasoning. Some reasoning contains minor errors but still reaches correct answer. Incorrect answers often have flawed reasoning. This suggests that reasoning quality is strongly linked to performance, but also model is not perfectly reliable. So chain of thought improves interpretability but does not guarantee correctness.
Now that we have analyzed how chain of thought prompting improves a performance across different tasks and how its effectiveness depends on model scale, I will now focus on understanding why this method works, where it works best, and what its limitations are. This slide analyzes performance across different subsets of MAWPS dataset, which vary in difficulty. The subsets include single OP, problems requiring only one arithmetic operation, single EQ, problems reducible to single equation, add sub, slightly more structured multi-step problems, multi-arith, complex multi-step arithmetic reasoning. Now the key observation from this slide is chain of thought provides minimal or negligible improvement for simpler subsets like single OP, but shows significant improvement for complex subsets like multi-arith. Why does this happen? Because simple problems do not require intermediate reasoning. The model can directly map input to output. However, for complex problems, the solution requires decomposition into multiple steps. And this is exactly where chain of thought helps. So the important takeaway from this slide is COT is beneficial when problem inherently requires multi-step reasoning. It is not universally helpful. Its effectiveness depends on depth of reasoning required. This slide is one of the most important in the paper because it tries to answer what does chain of thought prompting actually improve performance. Uh, to understand this, the authors perform an elevation study where they test different variations of prompting. Let's go through them one by one. Uh, First, equation only. In this variant, the model generates only a mathematical equation before the answer. Observation is that this does not perform well on complex datasets like GSM 8K. Reason is that the model first needs to understand the problem, and that itself requires reasoning. So equation alone is not enough. Second, variable compute only. Here the model is given extra tokens instead of reasoning. The purpose is to test whether more computation alone helps. Result is that there is no improvement, so more tokens is not equal to better reasoning. Third is chain of thought over after answer. Here reasoning is generated after the answer. The result is performance is similar to baseline. This shows that the model is not reasoning to arrive at the answer. So the final conclusion is that the improvement comes specifically from step-by-step natural language reasoning before generating the answer. So it is not equations, not extra computations, and not post hoc explanation. It is sequential reasoning process itself that drives the performance. This slide shows example of chain of thought reasoning across different types of tasks. We can see examples from arithmetic reasoning, common sense reasoning, symbolic reasoning, and now what is important here is not the specific examples but the pattern. In each case, the model breaks the problem into smaller steps, solves the intermediate parts, then arrives at the final answer. This demonstrates a key idea. Chain of thoughts acts as a general reasoning framework. It is not limited to math or a specific dataset. Instead, it works because natural language can express reasoning steps in any domain. So we can think chain of thought as a universal interface for reasoning in language models. This is why it generalizes across diverse tasks. This slide provides a practical guideline for using chain of thought prompting. Instead of just presenting results, it answers when should we actually use chain of thought. So the first condition is when the task is complex. The COT works best when the problems requires multiple reasoning steps. There is a clear decomposition. It is less useful when tasks is simple and direct mapping is sufficient. Second condition, model scale. COT is effective only for large models. Small models may generate incorrect reasoning, so large models can maintain logical consistency. So scale is a prerequisite. Third condition, need for interpretability. COT is useful when we want to understand model reasoning, debug or analyze outputs. So when not to use COT for simple classification tasks, for small models, when latency is computation or computation is a concern. Final, final insight. So COT is a conditional technique, not universal. Now let us discuss the limitations of this approach. First is that it does not prove true reasoning. Even though the model generates reasoning steps, it may still be pattern matching. So COT does not guarantee human-like reasoning. Second is reasoning can be incorrect. Sometimes final answer is correct, but reasoning is flawed, or vice versa. So interpretability is helpful but not perfect. Third is it requires large models. The biggest gains appear only at 100 billion plus parameter models, so it is not effective for small models. Fourth, no guarantee of correctness. Even with COT, errors still occur, so it improves reliability, but it does not solve reasoning completely. So the final takeaway is that chain of thought is powerful, but it is not a complete solution to reasoning in AI. Now I will conclude the presentation. The main contributions of the paper is that it shows that large language models already contain reasoning ability, but standard prompting fails to utilize it. The role of chain of thought prompting is that it enables step-by-step reasoning, improves performance across multiple domains, requires no additional training. Key insights: reasoning ability is emergent with scale, natural language reasoning is powerful, prompt design significantly impacts performance. Limitations: not always reliable, requires large models, does not guarantee true reasoning. So, prompting is not just input formatting, it is a way to unlock capabilities already present inside the model. Thank you for your attention. Uh, Thank you.
Good morning, everyone. Today we will be presenting on a topic that sits at the intersection of linguistic, computer science, and economics. Do all the languages cost the same? Tokenization in the era of commercial language models. This might sound like a simple question, but the answer has real world consequences on billions of people, all the people who interact with AI systems in language other than English. As AI becomes more commercialized, access is priced per token. Understanding how different languages are tokenized becomes more critically important, not just technically, but also from a fairness perspective. So let's get started. So let's start with the real world motivation. Modern large language model APIs like GPT, Claude, and Gemini all operate on fundamental pricing systems. They charge per token. So every time you send a request or receive a response, your bill will entirely depend on the number of tokens involved. A common example is something like 1000 tokens costing 1 cent. This immediately raises a critical question. If I write the exact same meaning in two different languages, do I pay the same amount? The answer, as we will show, is no. And that has serious implications. The diagram on the right illustrates the pipeline. Text comes in, gets broken into tokens, and then those tokens get turned into embeddings. The cost is logged at the tokenization step, kind of intelligence is applied.
To make this concrete, let's run a simple thought experiment. Take a sentence, I am learning machine learning. Now translate it into three structurally different languages, say Hindi, Chinese, and Turkish. Each of these languages has a fundamentally different grammar, script, and word formation system. The question is, will all three translations produce the same number of tokens? The answer is a clear no. Tokenization is heavily dependent on language structure. The same meaning expressed in different languages will generate very different token counts and therefore very different cost. This is the core puzzle we are exploring in this paper.
So here's the key insight. LLMs do not process words, they process tokens. Tokens are not same as words. They are subword units that the model has been trained to recognize. So the financial cost of using any commercial LLM API is direct mathematical function of token count. We can write it simply as cost equals a function of token. The conclusion follows naturally. If language A requires more tokens than language B to express the same thought, the language A is objectively more expensive to use. This is not a bug or an edge case, it is a structural consequence of how tokenization works, and it affects every non English speaker who uses these systems.
So, what exactly is tokenization? Formally, it is the algorithmic process of mapping raw text into a sequence of integer IDs called tokens, drawn from a predefined vocabulary. We can write this as text maps to a set of tokens T1 through Tn, where n is the total number of tokens. The primary goal is to create an efficient mathematical representation of language that neural networks can process. The challenge is balancing two competing demands: vocabulary size and sequence length. A very large vocabulary can represent words compactly but becomes memory intensive. A very small vocabulary keeps things lean but results in longer sequences. Tokenization algorithms try to find the right middle ground.
Modern LLMs don't use word level or character level tokenization. They use subword tokenization. The key idea is that words are broken into meaningful subunits. For example, the word unfriendly becomes un plus friend plus ly. Each piece is a token. There are two main reasons for this approach. First, it handles rare or out of vocabulary words gracefully. If the model hasn't seen a word before, it can still break it into familiar parts. Second, it keeps the vocabulary size manageable, typically in the range of 50,000 to 100,000 tokens. This makes training and inference computationally practical. while still covering a huge range of language.
Moving to common tokenization algorithms. There are three major tokenization algorithms used in this practice. First one is byte pair encoding or BPE. It starts with individual characters and iteratively merging most frequent adjacent pairs into single token. This is used in GPT-3 and GPT-4. The second one is word piece. It is similar to BPE, but instead of merging the most frequent pairs, it merges based on what maximizes the likelihood of the training data. It is used in Word. And the third one is sentence piece. It treats the entire input as raw byte stream, including spaces, which makes it language independent and it do not requires any pre-tokenization step. This is used in T5 and Llama. The most common thread across all three is frequent patterns get compressed into single token. So the rarer a pattern, the more tokens it requires to represent it.
Now, here is where language structure becomes crucial. Languages differ fundamentally in their morphology, script, and word formation rules, and these differences directly affect tokenization efficiency. English is an analytical language. It relies on word order and helper words, and many common words exist as a single token in the vocabulary. Turkish is agglutinative. It forms words by stringing together morphemes, which means a single word can pack a lot of meaning. This makes Turkish words long and unusual looking to an English trained tokenizer, leading to heavy fragmentation. Chinese is a logographic language where each character represents a single or distinct word or morpheme, giving high information density per character. Though script variation can still affect tokenization, these structural differences together are the root cause of the token count disparity we see across languages.
Now, this slide drives the point home with a sharp linguistic insight. In agglutinative languages, a single word can contain many morphemes, and the tokenizer has to split these heavily, resulting in significantly more tokens per meaning unit. Take the Turkish word everinizden. This single word translates to the full English phrase, from your houses. It contains morphemes for house, plural, your, and from, all fused together. An English trained tokenizer sees this as an unfamiliar long string and fragments it into smaller pieces, each getting its own token. What costs 1 or 2 tokens in English can cost 5, 6, or even more in Turkish. This is the morphological penalty in action.
This brings us to the central argument of the entire presentation. Tokenization efficiency varies widely across languages because token counts drives cost. The number of tokens per unit of meaning differs substantially depending on the language used, and therefore LLM commercial cost is not language neutral. This is not just a theoretical observation. It has direct, measurable financial consequences. Every developer or business building multilingual applications on top of commercial LLM APIs is exposed to this asymmetry, and every end user interacting in a non-English language is implicitly paying a premium for the same information.
To study this rigorously, the methodology follows four steps. First, select a robust multi-parallel multilingual dataset, one that contains the same content in many languages. Second, ensure exact semantic equivalence. We are comparing the same meaning across languages, so translation quality matters. Third, apply a consistent commercial tokenizer, specifically GPT's CL100K base, to all texts. This controls the tokenizer variable. Fourth, measure and compare token count, treating meaning as the control variable and token count as the outcome. This setup is clean and scientific. By holding meaning constant and varying only the language, we can isolate the effect of language structure on token count and therefore on cost.
Moving to mathematical framing and metric. To formalize this, the study defines tokenization efficiency E of L as the number of tokens required to represent a given semantic sentence in language L. If C is the cost per token and T of L is token count, then the cost of L equals to C times T of L. The comparison we care about is E of English versus E of some other language. Let's say Hindi. If T of L1 is greater than T of L2, then the cost of L1 will be greater than cost of L2. The math is pretty simple, but implications are significant. This framing lets us quantify how much more expensive one language is relative to another language, given some meaning.
The experimental results reveal a striking disparity. Some languages require 1.5 to 3 times more tokens than English to convey the exact same information. This is not a small rounding error, it's a factor of up to 3. And this has two cascading effects. First, it mathematically guarantees up to 3 times higher API cost for non English users. Second, and this is often overlooked, it reduces the effective context window. Since models have a fixed maximum token limit, non English content fills that window faster, meaning the model effectively forgets the earlier parts of the conversation very soon. So, non English users not only pay more, but they also get less capacity per request.
So now let's take a look at a concrete example. The sentence is I'm learning NLP. In English, it produces around 6 tokens. The same meaning, while expressed in Hindi, मैं NLP सीख रहा हूँ, produces roughly around 10 to 14 tokens. That translates to a cost ratio of approximately 1.6 to 2.3 times more expensive for Hindi users. The semantic content is identical. The computation required to understand the meaning is equivalent. But because Devanagari script is underrepresented in the tokenizer's vocabulary, each character or syllable gets assigned to its own token instead of being merged into efficient multi-character units. The conclusion from the slide is direct. Meaning stays consistent, but infrastructure cost rises significantly.
There are three root causes for this disparity. First, English heavy training data. Tokenizers learn from the corpora they are trained on, and English is massively overrepresented. So the vocabulary is optimized to compress English text efficiently. Common English words and phrases get single tokens, while equivalent structures in other languages don't. Second, fragmented scripts. Non-Latin scripts like Devanagari, Arabic, and Hangul are poorly represented in the vocabulary, so the tokenizers fall back to the character level or even byte level splits for them. Third, rare subword combinations. Agglutinative languages like Turkish produce complex morphological strings that are entirely outside the tokenizer's learned vocabulary, causing severe fragmentation into small, rare subword tokens.
We can verify this bias programmatically using OpenAI's tick token library, which is the actual tokenizer used in commercial GPT models. The code loads the CL100 base encoding used by GPT-4, then encodes two semantically equivalent sentences, one in English and one in Hindi. The result is striking. The English sentence, I love machine learning, encodes to just 4 tokens. The Hindi equivalent, मुझे machine learning पसंद है, encodes to 15 tokens. That's nearly 4 times more. This isn't an estimate. This is actual token count from the production tokenizer that commercial APIs use to bill users. The observation from the slide puts it directly. Hindi requires structural over fragmentation just to be processed by the model.
The visualization makes the trend undeniable. English sits at the baseline of 1.0 times. Spanish, a Romance language, comes at 1.3 times, still relatively effective because it shares Latin script roots with English. Hindi jumps to 2.5 times more tokens. Turkish reaches 3.0 times the token count of English for the exact same meaning. The interpretation is pretty clear, a consistent tokenizer bias. English maintains the lowest compression ratio, while non Latin scripts or morphologically rich languages suffer from highest token inflations. This isn't some random variation, it is predictable consequence of how and what the tokenizer was trained on.
The commercial API pricing is strictly token based, for example, around 1 cent per thousand tokens. This design choice directly translates into a financial consequence. This means that users interacting in a certain language end up paying more for the same task because their inputs are broken into more tokens. At the same time, they effectively get less semantic output per dollar that they spend. Now, what makes this especially concerning is the broader implication. This is not just a technical inefficiency, but it also creates a form of economic inequality at scale. People are being indirectly taxed because of the structure of their language. So if someone is building a application in a language like Hindi or Turkish, they are inherently at disadvantage compared to someone building the same system in English, not because of skill or resources, but simply because of how their language is tokenized. And that's what makes this issue fundamentally important. It's not just about models, but it's about the fairness and access to AI technologies.
So now from an AI ethics perspective, this is a structural fairness issue, not a problem with model accuracy or intelligence. The disparity doesn't come from how well the model understands the language. It arises much earlier, at the stage where the text is converted into tokens. Most AI ethics discussion focus on biased outputs like hallucinations or stereotypes. But here the bias is embedded deeper in the infrastructure itself, specifically in the tokenization process. Tokenizers like byte pair encoders are trained mostly on English data, making them highly efficient for English but inefficient for many other languages. As a result, the same meaning can require more tokens in underrepresented languages, increasing cost and sometimes reducing performance. This creates a subtle but important inequality where some languages are inherently disadvantaged before the model even begins the reasoning.
Zooming out to broader impacts, three patterns emerges. First, global inequality. Non-English users are systematically disadvantaged, which can slow down multilingual adaptation of AI technologies, especially in developing markets where cost sensitivity is higher. Second, the rich morphology penalty. Languages like Turkish and Finnish suffer drastically worse efficiency due to their agglutinative word formation. Every complex word is in these languages becomes a cluster of fragmented tokens. Third, and interestingly, complex structures exceptions. Some languages, like Chinese, can occasionally show better efficiency depending on how the tokenizers handle logographic characters, because each character carries a lot of meaning. The token per meaning ratio can sometimes be more favorable than expected.
Like any study, this one has important limitations. First, tokenizer dependency. Results vary significantly based on which tokenizer is used. Llama's sentence piece performs differently than GPT's stick token, so findings from one may not generalize to another. Second, translation quality variance. Ensuring exact semantic equivalence across 50 plus languages is genuinely difficult. An awkward or overall literal translation might artificially inflate token count, skewing results. Third, context specific variation. Token efficiency changes based on domain. Rare scientific or medical vocabulary might be over fragmented, even in English, which complicates cross language comparison in specialized fields. These limitations don't invalidate the findings, but they remind us to interpret results carefully.
So, what can be done here? Four directions are proposed. The first is multi-language tokenizer. Train the tokenizer on balanced multilingual corpora so the vocabulary represents all families, not just English. The second one is language aware pricing. Implement dynamic pricing multiplier based on the detected language. so the cost across different population can be normalized. The third one is character-based pricing, shifting the API billing from per token to per byte or per character, which is more closely related to actual semantic content regardless of language. The fourth one is novel architecture, exploring entirely token free models like byte level models like byte 5, which processes raw byte streams natively without any BP tokenization step, which eliminates the language bias at its root.
Now let's consolidate everything that we have discussed into the following key takeaways. First, tokenization is not neutral. It might seem like a purely technical processing step, but in reality, it is an algorithm trained on specific data distributions. Since most training data is dominated by English and Latin script languages, the tokenizer become inherently optimized for them. This introduces a subtle but important infrastructural bias even before the model starts learning. Second, language dictates token count. Different languages have fundamentally different structures, say in terms of morphology, grammar, and writing system. For example, agglutinative language combine many meanings into a single word, while some scripts are not efficiently represented in byte level tokenization. As a result, the same meaning can require very different number of tokens across languages. Third, tokens dictate cost. This is where the technical detail becomes practically important. Commercial LLM APIs charge users based on number of tokens processed. So if a language consistently requires more tokens to express the same idea, users of that language are efficiently paying more for the same task. This creates a direct and measurable financial impact. Finally, cost is language dependent. Putting it all together, we see that cost is not uniform across languages. Non English and underrepresented languages are often both more expensive and less efficient to process. This is not just a coincidence, but it is a structural consequence of how tokenization and pricing models are designed. And this is why the paper argues that solving this problem require rethinking tokenization strategies and pricing policies at a system level, not just improving the models.
And now we'll close this presentation with an open question for discussion. We've seen that the meaning does not translate to the same cost. Tokenization introduces a hidden layer of inequality in how users access AI systems. So the key question is, how should commercial AI labs address this imbalance? The study outlines three broad directions. One is to continue with token based pricing but improve tokenizer design to do better support for diverse languages. Another is to move toward character based or byte based pricing, which is more uniform across languages but may not align perfectly with computational cost. The third is language normalized pricing, where the cost is adjusted so that the users pay roughly around the same for the same amount of meaning regardless of language. Each of these approaches comes with trade offs in terms of fairness, technical feasibility, and business practicality. So now we'll end the presentation. Thank you.